Hello everybody. In this video we're gonna start talking about the one-dimensional steady-state molecular diffusion in case of having a chemical reaction. And in this case we will discuss two different types of systems. One system that's called a heterogeneous reaction, or where the reaction is a heterogeneous reaction, and the other is what we call a homogeneous reaction. The main difference between a homogeneous and a heterogeneous reaction is related to the phase in which the reaction takes place. If the diffusion is taking place, and let's take a look at this. So this is what we mentioned before about the two systems. We didn't mention the names of the homogeneous and heterogeneous reactions, but we mentioned the concept. And this has to do with the phase where the reaction takes place. So if the components are diffusing, and after diffusion is done and they reach the surface or the interface where the reaction takes place, let's say a surface of a catalyst or something like this, then this is a heterogeneous reaction. So the reaction is taking place not in the fluid phase, but it's taking place in a solid phase, which is this interface. And this is what we call the heterogeneous reaction. So in this case, the reaction is zero, and as we said earlier, the reaction is a boundary condition in this case. There is another option, which is the homogeneous reaction, which means that the reaction is taking place simultaneously in the same phase where the diffusion is taking place. So I have two components, they are diffusing from a point to another, and while they are diffusing, the reaction is taking place. And it doesn't need to go to this, or it doesn't occur at a surface where the reaction or the diffusion ends at. So in this case, it's called a homogeneous reaction, and the rate constant here, or the rate equation, is not equal to zero, or the rate term is not equal to zero. So this is the main difference between a homogeneous and a heterogeneous reaction. So let's see the case that we are gonna discuss, which is the one-dimensional system with chemical reaction. So the general continuity equation would be in this form. We just cancel the steady state, the unsteady state term, and then we have the rate equation. It might have any form, and as we said earlier, the rate equation is an equation that relates the speed of reaction to the parameters that affect the reaction, mainly the concentration of the reactant, sometimes the products, the temperature, the pressure, and many other parameters. Some of these parameters will be included here in the K, which include mainly the temperature. Sometimes it includes the other parameters. It includes also the activation energy, and there are other parameters included here. And this is the concentration, and this is the simplest form, the form that we see here, which is the first order reaction, which is is called the power law kinetics, and this is the first order reaction, which has C power 1. This is the form of the equation. So if we put everything together, so this is again this is the rate in case of a homogeneous reaction, where we'll put this as this term in the equation. But in case of a heterogeneous reaction, we will put it as 0, and the R is going to be a boundary condition. So we will not do more or different steps than what we did before. It's going to be the same procedure. So I'll go directly to an example where we will solve the problem and see how we can deal with it. So this example that we have here is about a catalyst particle that is suspended in a gas mixture, and it contains a species A that diffuses. So to understand what is this catalyst, it is a solid inert core, which is this circle. It's coated with the catalyst material, which is the black bold line. This is the catalyst, and it's coated with a porous solid material that has porosity of 0.6, and this is where the diffusion takes place. So this white annulus that we see here is the area of interest for us, and this is where the species A diffuses through from outside at concentration equals Ca infinity all the way to the surface of the catalyst. and this is where the reaction takes place and species B is produced and diffuses back to outside. So this is the surface where or the part of the catalyst material that the diffusion takes place. We have the diffusion taking place between R1 and R2, between 0.3 and 0.5 centimeters. The gases flowing are all around the catalyst material or the catalyst pellet. The concentration is kept homogeneous all in all directions, which is Ca infinity. And so this is the reaction that takes place at the surface of the catalyst, which is A goes to B. It's 1 to 1, and these are the radii. I have already mentioned them, and the concentration. This is an important part here. That the concentration of species A is CAS. So this is the concentration of species A at the surface of the catalyst. Of course, in this case of steady state, so the concentration is always constant, and the reaction rate at the surface equals Na at R equals R1 equal negative Ks CAS, which is the first law, first order reaction. And this negative sign here indicates that the flux is in the negative direction of R. So R increases outside, so this is going inside, so the flux is negative in the opposite direction of increasing R. So what we want to do now is to develop an equation to predict the flux of species A at the catalyst surface, and then compare the flux or calculate the flux at temperature 300 Celsius, 1 atmosphere, and Ks equals 2 centimeter per second, DAB equals 0.3, and I know the mole fraction of A outside, which I can use to calculate the CAS or the Ca infinity. So I know some decent information here that I can use, but now we need to start with the point that we are interested in, which is the mass transfer part, to get the flux equation. Once I get the flux, I can do anything else. So to get the flux, we have to use the first put our assumptions, which will be, first I will assume that I have I'm told that I have a constant source and sink of species A, because we have the concentration here is always constant, so it's a continuous source. It's consumed here due to the reaction, so it's a continuous sink. So it's case of steady state. It's one dimensional in R direction, which is what we can see here. We don't have any reaction or no homogeneous reaction. The reaction takes place at the catalyst surface, so R is 0, and the effective diffusion coefficient is gonna be the diffusivity that we have as a given in the problem multiplied by epsilon square. This is according to the diffusion in non-cylindrical porous materials. This is what we know from before. We know epsilon and we know DAB, so we can easily calculate DAE. And the temperature, pressure are constant, and we will use. I forgot to say something, that this photo that we see here is a cross section, and this is a problem that we will apply in two cases. That this cross section is of cylindrical catalyst particle, and the other is for a spherical catalyst particle. Both will have the same cross section, but one of them has cylindrical shape and the other has a spherical shape. So what we will do here is to solve it twice. Once for spherical shape and once for cylindrical shape, and we say here that the cylindrical catalyst, in case of cylindrical catalyst we will use cylindrical coordinates, and for cylindrical catalyst or spherical catalyst we will use spherical coordinates. So these are the assumptions that we have, and then we can go to the solution. So the solution is gonna start with the same steps that we are used to use. And here I want to mention something for those who are gonna check the textbook or compare this to what's in the textbook. The solution in the textbook is kind of hard to follow, because in the textbook he is solving the two cases simultaneously. So he does a step for the continuity equation. He writes the equation for cylindrical catalyst and the spherical catalyst together, and then for the next step he is gonna put the boundary conditions for both, and then he's gonna solve the equation with the boundary conditions. So you'll have similar equations, and it's gonna be kind of somehow hard to follow or kind of confusing. So I prefer to solve each one of them separately, so that we prevent any confusion that may happen. So this is what I'm gonna do here. The solution that I'm gonna do is simply to go with the continuity equation, apply the boundary, the assumptions. So you'll cancel the two terms of the theta and z. I'll cancel the time dependence, cancel the r. So the equation is this. So till now, this is part of the solution that, or the same steps that were done in the textbook. And from this we can say that n multiplied by r is constant. So this is the output of the continuity equation. In the solution, I want to show you the solution in the textbook because it was nice, but I think it might be confusing to some people, so I prefer to just go with the continuity equation. So this is what we get from the continuity equation for a case of cylinder, and this is for the case of sphere. In the solution in the textbook, the way he solved it is he assumed that, or he didn't assume, he said that the flux is not constant in this case. We are used to have the flux constant, but in this case the flux is not constant. So the other option that he suggested is to use a constant parameter, and the constant parameter is the rate. And if you think about this, if it's a steady state, then the number of moles going in is constant because it's a case of steady state. And for this constant rate, you will have decreasing area as you go from the big radius. As you go inside, the material is going into smaller area. So the flux would be larger. The rate is constant. The area is getting less, so the flux has to be higher. So this is very, very logical and very common sense, and that's why the area in case of a cylinder is 2 pi RL. So 2 pi and L are constant, so R multiplied by the flux is constant. So this is what we get from the continuity equation without going into these details. But in this case, he did the balance equation. He said that the area multiplied by the flux in minus area multiplied. So he started with the very first equation of derivation of the continuity equation. So he started with the area multiplied by the flux and the area multiplied by the flux, and he said that this is R plus delta R, and then he did the this difference and divided by delta R, and then the equation that he got is W, which is the rate, equals 4 pi R square NAR for sphere, and 2 pi R2L N in case of a cylinder. So this is the constant that he got. I didn't follow the same procedure, and the solution that I did is almost, or it's not almost, it's exactly giving the same answer as the solution that he did. I believe what I suggest is more simpler because it's not easy for anybody to go through this derivation. So I prefer to go with the same procedure. So what I did is I said, okay, so R multiplied by N equal constant. This is something that we haven't seen before, but I can say that the flux equals constant divided by R. So this is the first output from the continuity equation. Now I can use the general flux equation, which is this is the general form of the equation. I can say that NA equals negative NB because it is equimolar counter diffusion. I have diffusion of A and B going in the opposite side, so I can get this from the stoichiometry of the reaction, and then I can say that N equals negative D multiplied by dC by dR. Now I can put the two equations together, but before that I need to see the boundary condition. I have a boundary condition at R2 that C equals C infinity, and at R1 C equals CAS, and this is one point that I think might be kind of tricky here. The information that we were told here is that the concentration of species A is CAS at R1, and that the flux equals this. So you might think that it makes more sense to use this as the flux and just to know that C equals CAS at the surface, not to use this as a boundary condition. And this is totally is totally a valid suggestion. I'm gonna go first with the procedure of the solution in the textbook, and then next video I'll resolve the problem with the boundary condition of CA equals or the flux equals negative KCAS. But for now I'm gonna go for this boundary conditions as it is solved in the textbook, and now the N equals CAR from here, and N equals negative D multiplied by the concentration gradient, and from this we can do the integration from R1 at CS and R2 equals C infinity. And this is one nice thing about using constant boundary conditions, that you can use boundary conditions as limits of integration and directly do the integration, get the constant C1 from here. This is the value of C1, so I can use C1 here to get the value of the flux, which is this, and this is the flux equation of the species A in the cylindrical particle, and this is the flux at R equals R1. If it's not clear, let me zoom in here. This is the flux at R equals R1 is going to be D divided by R1 multiplied by R2 for R1 CAS minus CA infinity. So this is the flux, and now I can proceed to the next step where I have the formula of the flux, and if I want to use the information that I know, then I'll see that I'll not be able to calculate the flux, because I know the diffusion coefficient, I know R1 and R2, I know CAS, CA infinity, but I don't know CS. CS is not known, and I still cannot use this equation to calculate the flux. So I have to know or to calculate the value of CAS. So to do this, we will use the information of the rate. So this is where we will use the rate equation. So I will apply this equation or solve them simultaneously to get CAS as a function of the rest of the parameters. So if we put or equate these equations, then with some mathematical manipulations, it's not hard, but it's just a long process. It's not very long, but it's just mathematical simplifications. So we'll have the flux taking this form, D multiplied by K multiplied by C infinity divided by D plus this term. Now we can apply the information that we have for the flux and for the diffusion coefficient for Ks and Ca infinity. C infinity can be calculated from the ideal gas rule. It's P divided by RT, and P equals Y multiplied by P, which is Dalton's law, and this is the value of Ca infinity. We have diffusion coefficient, we have the flux can be calculated to be this value. So this is for the first part of the equation or of the problem. The second part is gonna be pretty much the same, with only one difference, is that it is spherical in shape. So the continuity equation would be this. We will cancel the rest of the terms, and then the equation would be this shape, which means that R square in AR equals C2. Again, I'll say that N equals C divided by R2, R square, I'm sorry. And then with the flux equation, we will have the same boundary conditions. We will do the integration, but of course this is R square, it's not 1 over R, so it's gonna be 1 over R1 minus 1 over R2. And this is, by the way, the shape that's very common in case of spherical shapes, and the cylindrical will have ln R over R. This is something that you see in heat transfer, you'll see in other cases. And then this is C2. We substitute with C2 to get the shape of the equation of the flux, and this is the flux in case of R equals R1. Again, we'll have the same problem. I know everything except for CAS, so I need to do something to calculate the value of CAS. So I'll substitute with the flux equation, solve the two equations simultaneously, do some mathematical simplifications to get CAS, and then substitute with CAS here, and then the equation will be, after some simplifications, would be like this. So this is the flux. So if this shape. So if I use this equation to calculate the flux, then the flux would be calculated to be like this. So this is the solution to this problem. In the next video, we will continue talking about this exact same problem. We will talk more about the other solution and some outputs that we can get from the equations that we got from this solution. So I believe it's pretty helpful. So I'll see you then, inshallah. Goodbye.